Hi, I'm Jonathan Aldrich. Let's talk about type systems. What is a type? There are three views that we could consider. The first view is denotational. It interprets a type as a collection of values from a domain. For example, the 32-bit integers might form the type int, or the real numbers, representable as IEEE single precision floats, might be represented as float. A second view is the structural view. A type is a description of a data structure in terms of fundamental constructs. So for example, a point is a record that's made up of fields x and y, both of which might have type int. Finally, there's the behavioral view. A type is the set of operations that can be applied to an object. So for example, a stack might have operations push and pop. Compared to the structural view, the behavioral view focuses on what are the operations and what are their behavior, rather than the structure of how data is stored in the type. So why do we have types? What are they good for? Well, recent research has shown that one of the primary benefits of types for programmers in practice is documentation. What do we need to pass to some library function? This is the result of some of my research, in fact, as well as that of some others. Types also provide an implicit context for compilation. How do we know whether this plus operation should be an integer addition or a floating point addition? Well, types can tell us. Finally, types can check that meaningless operations don't occur. Can we subtract 5 from hello world? Probably not. It doesn't make sense. So type checking can prevent a lot of simple errors. It can't prevent all meaningless operations, but it catches enough of them to be useful. Let's talk about some terminology. We talk about type safety or type-safe languages, which are languages designed so that only type-appropriate operations are ever applied to an object. This can be enforced either statically or dynamically. And so at the bottom of the screen, you see we have static versus dynamic typing, which tells you whether the types are checked at runtime or at compile time, with static meaning compile time and dynamic meaning runtime. Finally, there's strong versus weak typing. And that is really the degree to which the language enforces typing invariance and prevents accidental errors. This is more of a spectrum than a hard distinction, and we'll look at some examples. So Java is type safe. It ensures that all operations are safe on the types they're applied to. It's statically typed because type checking is done at compile time. And it's a strong type system because it ensures a lot of strong invariance about the types that programmers deal with. Common Lisp is also type safe and strongly typed, but it's dynamically typed. Really, dynamic checks are used to make sure that operations are only performed on types to which they apply. Finally, C and C++ are strongly typed. They enforce some powerful invariance. They're checked statically, but they're not yet fully type safe. There are ways to get around the constraints of the type system and do unsafe things. JavaScript is another point in this space. It's type safe, dynamically, much like Common Lisp. It's weak, but it's weakly typed. The invariants it enforces are relatively weak. And of course, the enforcement is dynamic. Why is JavaScript weakly typed, whereas the others are strongly typed? Well, JavaScript allows many implicit conversions between types, and some of those can be very surprising. And so we would say on the spectrum, it's more on the weak side than the strong side. To give you an illustration of this, consider the following expressions in JavaScript. What do you think they evaluate to? If you'd like, stop the video and start a JavaScript interpreter like Node.js and try them. So here's what you may find if you tried it. The empty array is equal to the not of the empty array. This seems weird. You would think that you'd never have an equal sign with not on one side and the same thing but without the not on the other side, and it would be equal. But in fact, in JavaScript, this is what happens. The not operation coerces the array to a Boolean. And an array is considered truthy in JavaScript, and so the not array is false. But JavaScript always compares values of the same type, and comparing an array to false doesn't really work. So JavaScript will convert false to 0, and it will convert the array to the empty string, which converts to 0. And so that's why this equation is true in JavaScript. This concatenation of a few strings actually turns into banana. It's kind of a surprising way to write banana. How does it work? Well, we've hidden a little plus a operation in there. And in addition to concatenating the strings together, the plus a converts a into a number. Well, since a is a letter, not a sequence of digits, it's converted to NaN, or not a number. And that, of course, converts to the string NaN. So that's how we get banana from this. Finally, we have these three examples. Null equals 0 is false. Null is greater than 0 is false. And so you would think that null greater than or equal to 0 would also be false. But in fact, it's true. Why? Well, it turns out that equality treats null specially. And that treatment is not the same as the comparison operators. What equality does is it converts null to undefined for comparison. And so undefined is not equal to 0, because 0 is defined. On the other hand, the relational operators just convert both sides to numbers, and null is converted to 0. This explains what's going on here. For more fun examples, you can look at the website that I linked in the previous slide, WTF.js, which has a lot of interesting examples of the craziness in JavaScript. Some of these conversions were put in to make things convenient for programmers, and sometimes they are, but when they produce surprising results like this, it can also cause errors, and that's the danger of weak typing. Let's talk about different classifications of types and examples of those types. Discrete types are those that are sort of easily countable and are typically ordered. We have the integers, we have booleans, true and false. We have characters like a, or the new line character, or at, or space. And we have enumerations defined by the programmer, such as the weekdays, Sunday, Monday, Tuesday, through Saturday. Finally, we have subranges. So we might have a range of the integers between 1 and 100. Scalar types are sort of one-dimensional types. They include all the discrete types, but they might also include rational numbers and real numbers. Finally, there are composite types, which are composed or made up of other types. These include records, like we might have a point record that has x and y fields, both of type integer. We might have data types, or variants, or unions. So an address might be a union of a street address or a post office box address, because we can talk about addresses in either of those ways. We have arrays, which are constructed out of some base type and form a whole array of them. We have strings. Typically, a language has a built-in string type. It might be string in Java. Some languages have built-in set types. Others have library types that are sets. But either way, a set is composed of some other type. A pointer type is also a composition in a way, right? Because we have a pointer to some other kind of thing. In fact, we can even do this recursively. We can have a pointer to an int, but that's sometimes called a handle. We can also have lists. And again, this might be a built-in type like int list in ML, or it might be a library type like list of int in Java. Finally, files might be a type. These could be, again, library types like file pointers in C, or they could be Pascal's file of character. An important consideration in type systems is orthogonality. The basic idea of orthogonality, as mentioned earlier in the course, is that there are no restrictions on the way that types can be combined. This is very flexible for the programmer, and it also makes types easy to study if we represent them orthogonally. So in the study of type systems, or what we call type theory, we typically study orthogonal type constructs, so we can isolate different features of types from one another. We might provide a grammar of types, and then that grammar can be constructed in any way. Most practical languages, however, put some restrictions on orthogonality. Usually you want the language to be fairly orthogonal, but for practical reasons, like minimizing syntactic overhead or making type checking decidable, we might put some minor restrictions on orthogonality. For example, the ML language has what's called let-bound polymorphism. It means that it only allows polymorphism when we bind a name with let or similar constructs. Similarly, Java classes are a construct that combines different features, including records and recursive types, together. The package of a class is actually simpler and easier to deal with than if we used records and recursive types as their own particular constructs. Recursive types by themselves are notoriously complicated both in practice and in theory. So classes simplify things a bit. Another important concept in type systems is subtyping. Subtyping describes when one type can be safely used as another type. For example, In most languages, an integer can be used as a real number. And mathematically, we would say that integers are subtypes of reals. This is kind of an operational definition of subtyping. It's what the language actually lets you do with types based on their subtyping relationships. We can try to pin this down a little bit more carefully. An intuition behind subtyping is that A is a subtype of B, which we write with A less than colon B, if A conceptually is a kind of B. So a street address is a kind of an address. That forms design guidance for us, but we haven't yet pinned it down precisely. So again, there's three views that correspond to the three views of types, and we can form a more precise definition by looking at those views. So in the denotational view, remember, types are sets of values. And so a subtyping relationship is when type A describes a subset of the type values that B describes. For example, the integers are a subset of the reals. Therefore, it makes sense that integer would be a subset of type real. The structural perspective says that A is a subtype of B if A has all the structure that B has, and maybe some more. So a street address would have all the fields that address would have, like a city and a postal code, but it would also have a street and a house number. Finally, a behavioral notion of subtyping says that A is a subtype of B if A has all the operations that B does, and they behave as we expect to for a B. We can define subtyping rules using the same formal notation we studied in Chapter 4. Subsumption is the key rule that shows how you can use subtyping. It says that a subtype can be treated as a supertype. So if we have an expression of type tau1, and tau1 is a subtype of tau2, we can also treat expression E as type tau2. That's in the T subsum rule. Subtyping is generally reflexive and transitive. Every type is a subtype of itself because you can assign from that type two variables of that type. Subtyping is also transitive. So if T1 is a subtype of T2 and T2 is a subtype of T3, then T1 is a subtype of T3. Finally, we can capture some of Java's other subtyping rules as shown on the right. So an int is a subtype of long because long represents a larger set of integers than int does. Similarly, long is a subtype of float, and float is a subtype of double. This last relationship makes sense because double is higher precision than float, so everything that can be represented as a float can be definitely represented as a double, whereas if you went the other way, you might lose some precision. Technically, we lose a little bit of precision when we go from long to float because we might lose some of the low-order digits of the long number, but generally this is considered acceptable because float will capture the magnitude of the long quite well. But this is a thing to be cautioned about, that subtyping may not be fully semantically true if you need to represent numbers precisely, in which case, always use a long. Let's do an in-class exercise to illustrate these subtyping rules. Let's construct a derivation that types the expression 1 plus 2.5. You can use any of the following rules that I showed on the previous slide in your derivation. Go ahead and press pause for more time, get out a piece of paper, and see if you can come up with a derivation that types that expression using these rules.